All right, so no, I don't want to switch the tablet. No, leave me alone, you stupid computer. What we're going to do today is learn some transformations for the source side of our three-phase circuits and the load side of our three-phase circuits. So let's first talk about transformation of balanced sources. And let's consider a balanced three-phase Y connected voltage source. So something like this. Call this VAN, VBN, and VCN. And therefore this is terminal A, B, and C. And let's consider the case where VAN is equal to some phase voltage magnitude with an angle of 0 degrees. VBN is that same magnitude with an angle of negative 120 degrees. And VCN is that same magnitude with an angle of negative 240 degrees. Okay. So how could we determine our line voltages for this source? So particularly, let's call this guy VAB. How would we get that? So VAN minus VBN. Yeah, just using, how did you do that, Ian?
You just call it a KVL around the top node or loop.
Absolutely right. Kirchhoff's voltage law around the top loop. So the potential difference between this point and this point is simply the sum of these two voltage drops. Since we see the positive polarity terminal first, we're going to have VAN plus negative VBN, or simply VAN minus VBN. 100% correct. So let's write that down like so. Now we know that the quantity VBN is literally identical to the quantity VAN, just phase shifted by exactly 120 degrees. So from this, we can say that this is VAN multiplied by 1 angle 0 degrees minus 1 angle negative 120 degrees. Everybody okay with that? Well, this result is just a complex number, which happens to be square root of 3 with a phase angle of positive 30 degrees. So this is letting us transform our phase voltage in this balanced Y-connected load to our line voltages, right? Using this simple relationship, we can see that VBC is just VBN times that same conversion factor, and VCA is VCN multiplied by that same conversion factor as well. So if we were to connect a load to this source, could it distinguish the difference between being supplied by these line voltages for a Y-connected source? Could it distinguish between that scenario or just having a delta connected source directly? No. There is no difference between these two things, right? So we can actually say then that we can convert from our Y-connected source apologies. A, B, and C, we can convert in this way just by multiplying our phase quantity, Vp, times the conversion factor of square root of 3 angle 30 degrees. To get a delta connected source representation. Where this is terminal A, B, C, and this voltage VAB is simply VAN times root 3 angle 30 degrees. This voltage VBC is simply VBN times root 3 angle 30 degrees, etc. And here's where VCA is. All right, so we can convert a Y source to a delta source by simply multiplying our phase voltages by square root of 3 angle 30 degrees. That's not really our problem then. What we need to do now is figure out how to convert our phase voltages, which happen to be line voltages, for our delta connected source to an equivalent Y voltage. Any thoughts? It's the obvious answer. Yeah, divide by that exact same conversion factor. That is it. So to go the other direction, we take our line quantities, which I'm going to call VL, and multiply by 1 over square root of 3 with an angle of negative 30 degrees, which is the exact same thing as dividing by that same conversion factor. So this is what allows us to go back and forth between a delta connected source and a Y connected source, depending on what is most convenient for our analysis techniques. Okay. Those transformations are fairly straightforward. Yeah, I think I can leave that alone unless you guys want me to literally spell out exactly what it is, but it's just multiplying and dividing by this common factor. All right. So slightly more difficult is the transformation between balanced loads. And it's only more difficult from a derivation standpoint. All right. So let's say that we have, actually, I'll draw it the way that I prefer to. The following three-phase Y-connected load. B and C. Call this ZYA, ZYB, and ZYC. And we have a delta connected load. Here's Z delta C. Z delta A is between the A and B terminals. Z delta B is between the B C terminals, and then Z delta C is between the C and the A terminals. Okay. So if we were to determine the impedance seen between the A and B terminals of the Y load, which I'm going to call ZAB, what would we have? Simon, thoughts? I'm looking in between this terminal A and this terminal B and trying to find my equivalent impedance. What do I see? This says ZYA, this says ZYB, this says ZYC. Anybody else? Pardon? Which two? Exactly right. So just to be clear here, we have a network. Let's treat it as if they were resistors. My stylus will draw, which it's being difficult about. Let's call this guy A. Let's call this guy B. This is terminal C, so this would be RC, RA, and RB. When I look in between A and B, I just see this guy in series with this guy. RC doesn't show up because it's not connected to anything, right? That's the exact same situation I have with those impedances. So we have simply ZYA plus ZYB. Now let's look at the impedance seen between terminals A and B for our delta connected load. Justin, what do we see? Between A and B. So we're looking in right here. This is not a Thevenin, well, I mean, I guess technically it is, but this just is an equivalent resistance or equivalent impedance. So this is like, you should have learned to do this in engineering 120. Luke, take a crack at it. So these are deltas, but I think you're getting close. Okay, so we have this guy directly between terminals A and B, and it's going to be in parallel with a series combination of these two, which is, I think, what you were saying. So that would look like Z delta A times Z delta B plus Z delta C divided by Z delta A plus Z delta B plus Z delta C. Okay. So we can equate these two expressions if we want to find an equivalence between these two networks, right? So if the equivalent impedance of the Y-connected network between A and B is equivalent to the impedance of the delta connected network between A and B, what we get is ZYA plus ZYB is equal to Z delta A times Z delta B plus Z delta C, all divided by Z delta A plus Z delta B plus Z delta C. And we can develop similar expressions for what we see between terminals B and C, which is going to give us Z delta B times Z delta, let me erase that, A plus Z delta C here. Same denominator, denominator, Z delta A, Z delta B plus Z delta C. And finally, ZYC plus ZYA is going to look like Z delta C times Z delta A plus Z delta B divided by Z delta A plus Z delta B plus Z delta C. Okay. All right, so let's say that I know what my impedance ZYA, ZYB, and ZYC is. My unknown quantities are then Z delta A, Z delta B, and Z delta C. So I have a three equation, three unknown system, which can be solved, which tells me how to transform from a Y to a delta. I used to make you guys do this. I say you guys, Circuits 2 students, do this by hand. It's a terrifying amount of algebra. I then started making you guys do it with MathCAD, which is significantly easier in my opinion, but still a bit of a pain in the ass because you guys can't seem to figure out how to do solve symbolic equations. So instead I have just adapted I'm going to give you the results. All right. So to go from Y to delta, what we get is Z delta A is equal to ZYA times ZYB plus ZYB times ZYC plus ZYC times ZYA, all divided by ZYA, Z delta B is that same numerator divided by ZYB. So I'm going to be lazy. I have to talk and you guys don't, so I don't take it's cheating. And finally, Z delta C is the exact same thing, except that we have ZYC in the denominator. Okay. So this is a Y delta conversion for impedances. Okay. Where, to be clear here, let me scroll up. The impedances that we have found fall between the terminal pairs in the exact same way that I have drawn things up here. Okay, so if you wanted to apply this, in my opinion, the best way to do it is to label your terminals A, B, and C, and then put in the new thing between terminals A, B, and C, right? So, very similar to how I encourage you guys to do a source transformation. This is a transformation, literally disconnect your original network, do the transformation, and then replace the original network, making the exact same terminal connections as you had previously. So before we move along to the transformation in the opposite direction, let's talk about this for a moment. If we had a balanced Y load, what is the relationship between ZYA, ZYB, and ZYC, Mr. Bodie? Sarah, they are all identical. So this just looks like ZY squared plus ZY squared plus ZY squared, or 3ZY squared divided by ZY just gives me 3Z. So for a balanced three-phase load, we find that Z delta is simply 3ZY. This is still useful. Yeah. Definitely still useful, because when we talk about unbalanced three-phase systems, those absolutely apply, for sure. All right, so
That means that next loads in a delta configuration, they effectively become 3 times as lumpy. Or rather, the power.
so we'll get into those relationships. It's sometimes it can be tricky depending on the impedance of the loads and things like that with those relationships. So let me see if I can make a general statement here. They are equivalent loads, okay? Electrically equivalent, which means they should be consuming the same amount of power. So they're going to mess with the voltage and current relationships in a particular way to satisfy that. Does that make sense? The whole point of electrical equivalency is that it has the exact same terminal voltage, the exact same currents, and consumes the exact same amount of power. If those aren't true, they're not electrically equivalent.
You can have bigger individual loads to make up.
Right. Okay. So if we look at these 3 equations again, but now we consider that we know Z delta A, Z delta B, and Z delta C are unknown quantities for ZYA, ZYB, and ZYC. And so we could use a rigorous amount of algebra or MathCAD or rely on my results and find that we can express our Y quantities in terms of our delta loads. So this is a delta to Y conversion. Where ZYA is Z delta A, Z delta C divided by Z delta A plus Z delta B plus Z delta C. ZYB is Z delta A, Z delta B divided by that same denominator. And finally, ZYC is Z delta B, Z delta C over that same denominator. And for a balanced three-phase delta connected load, Caleb, what does it mean when my delta load is balanced? All the impedances are the same, absolutely right. So we have Z delta squared over 3Z delta. What does that reduce to? Z delta over 3. Or ZY is equal to 1/3 Z delta. So to go for a balanced three-phase load, to go from Y to delta, we multiply by a factor of 3. To go from delta to Y, we divide by a factor of 3. Okay. So we now have our different transformations that we need that we can use to make any circuit behave like a YY circuit, which is trivial to analyze using that equivalent circuit that we developed at the end of last class. So example problem time. Yes, indeed. We finally get to do math. You guys should be so excited. What? Yeah, fair enough. So I'm going to give you guys, that noise is aggressively loud. I'm going to go close the door. They're going to be unloading equipment, so probably for hours. All our new equipment for our power line upgrade is tired. They decided to interrupt my class to move it into the. So, all right. Anyway, I typically assign three-phase problems as word problems, effectively, where I describe what is going on. So I'm going to do just that. So this is the exact format that you should see your homework problems in. So it might say something like, in a balanced three-phase load, or excuse me, a balanced three-phase delta Y system, the source has an ABC or positive phase sequence. The line and load impedances are 0.1 plus J 0.1 ohms and 10 plus J4 ohms respectively. If a line voltage at the source is VAB is equal to 208 angle 0 degrees VRMS, determine the line voltages at what? So until you get comfortable with these type of problems, I'm going to draw a picture that represents what's happening, okay? So when I tell you that I have a delta Y system, what does this mean? We talked about this on the first day of class when we were discussing these things. Source is delta, load is Y. Absolutely right. So that's going to look something like this. Here is our A, B, and C terminal. This voltage is VCA. This voltage is VAB. This voltage is VBC. We have a non-zero line impedance. I'm going to represent that with an impedance here, ZW. Connecting the A phase of my source to the A phase of my load. I'm going to have the same ZW connecting the B phase of my source to the B phase of my load. And a third instance of ZW connecting the C phase of my source to the C phase of my load. And then finally, I have my Y connected load. Where the A, B, and C phases of this impedance are all what I'm going to call ZY. And I'm going to write down my known information over here. So I know that VAB is equal to 208 angle 0 degrees volts RMS. I know that ZW is equal to 0.1 plus J 0.1 ohms. And I know that ZY is equal to 10 plus J4 ohms. So does that effectively summarize my problem statement information? What am I asking you guys to determine? Which would be what? What we call them. So capital VAB, capital VBC, capital VCA. Justin. So we have a balanced three-phase system, which means for the system to be balanced, all of our ZYA, ZYB, and ZYC components of our load have identical impedances. It also necessitates for the system to be balanced that our transmission line impedances are the same thing across all three phases. All right, so what we are trying to find is this quantity VAB, this quantity VBC, and this quantity VCA. When I ask you for the line voltages, I want all three of those things. Okay. So can we apply our single phase equivalent circuit to this circuit as it is? No, because it's not a YY circuit. Our single phase equivalent circuit is only applicable for a YY system. How do we make this guy look like a YY system? Transform the source to a Y-connected source. Absolutely right. So I'm not going to bother redrawing this guy with a Y-connected source. But what are we going to do? So we're given VAB, right? So if we know VAB, how do we get VAN? Exactly right. This is simply VAB divided by the square root of 3 angle 30 degrees, or multiplying by 1 over the square root of 3 times negative, or angle negative 30 degrees. So in doing this, we should find that we get 120.089 angle negative 30 degrees volts RMS, which is traditionally called just 120 volts RMS. This building that we're in right here, the electricity is distributed in what's called a 208/120Y configuration, where we have access to 208 volts line to line and 120 volts line to neutral, or Y connection. That's what our power lab is set up for and all that kind of good stuff. So that's a very, very common configuration. If you look at the panels in this building, I know the ones in Bogart actually say it on the outside. It'll say something like 208/120Y. That's telling you what kind of three-phase power you have. If you have a Y configuration, you effectively always have access to a delta configuration too, because it's just looking at the voltages in a slightly different way. All right. So our three-phase equivalent circuit is going to look like this. Excuse me, our single-phase equivalent circuit. My apologies. Here's VAN, which we know. Here is ZW, which we know. Here is my capital A terminal. Here's ZY, which we know. Here's capital A. So what can we use this equivalent circuit representation to solve for directly? A couple of different things, right? We can figure out what our phase current is, or excuse me, what our line current is, IAA. We can figure out what our phase current is, IAN. We can figure out what our phase voltage is, VAN. Are any of these three quantities actually what we're looking for? No. Okay. But I would argue that if we can figure out the phase voltages in our load, like this guy right here, VAN and VBN, it should be rather trivial for us to determine the line voltage VAB. It's going to wind up being literally the exact same transformation that we developed for the sources. So with that in mind, how do we determine VAN? Coy, you have any thoughts? There is absolutely nothing wrong with that. I'm going to be slightly lazier because that's going to be a two-step process, and I'm just going to use voltage division, right? So Coy's suggestion was that we combine ZW and ZY into a single impedance, find our line current, which is the exact same thing as our phase current, and then use Ohm's law to find our phase voltage from our phase current. Or we can be lazy and do it in one step, utilizing simply voltage division, which is the route that I'm going to go. So V capital A capital N is going to be simply V lowercase a lowercase n multiplied by ZY over ZW plus ZY, which I find to be 118.655 angle negative 30.293 degrees. Volts RMS. And if we are, let's call it unaware or uncomfortable with using our transformations, how would we determine quantity VBA? You're putting too much work into it. Subtract 120 degrees from this angle, full stop. And we could continue on with VCN as well if we needed to. But VAN and VBN are the only two things that I actually need to know in order to calculate the quantity VAB. Where this VAB, the thing I'm actually looking for, is simply VAN minus VBN by doing Kirchhoff's voltage law around this loop. So let's see, VAB is VAN minus VBN, which gets me 205, what the heck just happened? 205.517 with an angle of negative 0.293 degrees. Volts RMS. Just to make me feel better, verify that capital VAN, which we solved for previously, multiplied by √3 angle 30 degrees gives us that exact same result. No. No, you haven't. Not trying to be rude, but you got it totally wrong. Capital letters mean that we're dealing with load quantities. Lowercase letters mean that we're dealing with source quantities. So if we look here, everything on the left-hand side of our circuit, which is the source, is expressed in terms of these lowercase terminal values, right? So VAB, lowercase a, lowercase b, is the potential difference between terminal lowercase a and terminal lowercase b, where the first letter in the subscript represents the positive polarity terminal, and the second letter in the subscript represents the negative polarity terminal. That is true for literally all of these voltages. On the right-hand side, on our load side, our terminals are given capital letters to differentiate it from the source side, but our voltages are defined in literally the exact same way. So this voltage VAB is the voltage seen between the A terminal and the B terminal, with the positive polarity terminal being A, the negative polarity terminal being B. This voltage VAN is the potential difference between the A terminal and the neutral terminal, which is the point of connection for our three phases in a Y-connected load. So I didn't explicitly state this to be the neutral terminal, but it absolutely is the neutral terminal because we have a Y connection. So just make it slightly easier, put my N terminal there. Okay. All right, so I believe that you guys verified that these two operations give us literally the exact same result, which means if you're following along, we don't ever actually need to know this VBN phase voltage. We can find only the phase voltage in the load and then use our conversion factor to go from a phase voltage to a line voltage, because that's actually how our transformation was defined. All right, so Luke, how do I get VBC? Too much work. Take this value, subtract 120 degrees from the angle. If you're doing any math other than shifting things by 120 degrees, you're putting literally too much thought into this. Once we know how the A phase behaves, we don't need anything else except rotating by 120 degrees to figure out how the B phase behaves, and an extra 120 degrees to a total of 240 to figure out what's going on with the C phase. Don't do more math than you need to. In a balanced three-phase circuit, all of these things have to have exactly the exact same magnitude, and their phase angles have to be separated by 120 degree increments. Okay. So VBC would become 205.517 angle negative 120.293 degrees volts RMS, and VCA would be 205.517 angle negative 240.293 degrees volts RMS. All right, how did you guys feel about this? Anything wildly difficult here? Not particularly. I hope not anyway. What if I'd asked you for a different quantity? Okay, so let's talk about some of the different things that I could have asked you for in this circuit, right? I could have asked you for the line currents. As I believe it was Coy pointed out, the line current is simply this voltage VAN divided by these two impedances connected in series. That's a pretty trivial calculation. The phase currents at the load is the exact same thing as the line currents. So that's a pretty trivial calculation. We were given the phase voltage at the source, and for a delta connection, that is the same thing as the line voltages at the source. So there's no work involved there literally at all. What about our phase currents in our source? What if I asked you guys for this current IAB, this current IBC, and this current ICA? Any thoughts on how we might approach solving for those quantities? So I'm going to draw this guy real quick. This is my line current IAA. Do we all understand how we could calculate that? Christian, tell me how we do it. I know I literally just said it 2 minutes ago, but tell me what you do. For the line current IAA. Right.
So if you did,
Absolutely right. 100% correct. Simply taking this quantity VAN, which we know, dividing it by ZW plus ZY will give us this line current IAA. Okay. So us knowing the value of that line current IAA is actually the only thing we need to know to figure out IAB. But apparently you guys don't see it just yet. That's okay. KCL at that node, 100%. So at this node right here, what's the current flowing out? IAA, our line current, and IAB, an unknown phase current. What's the current flowing in? ICA. So we have one equation and two unknowns, but I'm saying that we have enough information. For a balanced three-phase system, we do. Okay. Exactly right. So we can represent IAC, or excuse me, ICA in terms of IAB, giving us only a single unknown quantity, right? So let's go through the motions here and perform this analysis. Okay. So IAA, as both Coy and Christian pointed out, is simply the quantity VAN divided by ZW plus ZY. Somebody tell me what that is, because I didn't bring my calculator. I don't have notes for this. I just wanted to point it out how to do it.
-11.017. -52.0943.
2.094. RMS. Can anybody else verify that for me? All righty. So performing KCL up here, just to remind you, we're going to say that ICA is equal to IAB plus IAA. A little bit of rearranging is going to give us IAA, which we just determined is equal to ICA minus IAB, which is the same as IAB multiplied by a factor of 1 angle negative 240 degrees minus 1 angle 0 degrees. Which, if I am not mistaken, will come out to be square root of 3 angle negative 30 degrees. But it's been 6 months since I did this. There is a distinct possibility that I'm incorrect. So by all means, check. Root 3 angle negative 30. Okay. I'm 180 degrees off. So I messed up a negative sign in my head somewhere. Not a problem. Okay. So let's come around over here. What is the result of this? Actually, let's see. So we know IAA, we're trying to figure out IAB. So that means that actually, let me back this up a little bit. AB, in this case, is going to be IAA divided by, Ian, you said it was √3 angle positive 150? 150 degrees, okay? I can't do 11.017 over the square root of 3 in my head, but the angle should look like negative 202.094, which would be positive. See, add 360 to negative 202. Well, anyway, your calculator could do that too.
Yeah, 6.361 angle 157.1.
RMS. All righty. Okay. So is there literally any quantity in this circuit that I could ask you for that you can't figure out at this point? The hardest one to do are these phase currents, which is literally just Kirchhoff's current law. The circuit analysis that we're doing in these circuits isn't supposed to be difficult, legitimate, not supposed to be hard. The only hard part about it is remembering all of these things have the same magnitude. They're just shifted by 120 degrees. Without that understanding, this stuff is literally impossible to do. Or I guess not necessarily literally impossible, but would require setting up systems of equations and all that kind of stuff, which are completely and utterly unnecessary with that small amount of understanding. Okay. All right, so what I've got in store for, what day of the week is today, Wednesday? What I've got in store for Friday will be a couple of example problems. I am also going to go upstairs literally right now and upload a homework set on this kind of good stuff. And so I'm going to have an example problem or two prepared for you guys for Friday. If you have any questions about any of the homework stuff, let's go ahead and knock that stuff out. And then on Monday, we are effectively going to try to wrap things up or come as close as possible to it by talking about our three-phase power relationships, which is just going to be just, remembering when to multiply by square root of 3 and when to divide by square root of 3 effectively. All right, that's enough out of me for today.